2014. Stanford is watching Google eat their lunch. Word2vec is everywhere. Nobody at Stanford loves that Google is claiming the trophy for word embeddings because Stanford has been doing count-based semantics for 20 years. So they build their own method, different math, different philosophy, different everything, and they get almost the exact same vectors. That's either a coincidence or it's a clue. The paper is Pennington, Socher, and Manning. GloVe, Global Vectors for Word Representation. The title is basically a shot at word2vec, which use local context windows. Stanford's argument was, you should be looking at the whole corpus's co-occurrence statistics, and when you do, you get vectors just as good, sometimes better. That should tell you something important about what embeddings actually are. Last video I told you, word2vec worked by predicting nearby words. Neural net, gradient descent, negative sampling, very machine learning, very Google. What I didn't tell you was that there was a whole other tradition in linguistics, going back to the 1990s, that had been building embeddings a completely different way. By counting, not predicting. Counting how often word A appears near word B in the entire corpus. Today's puzzle. If two totally different methods, one predictive, one count-based, end up producing near-identical word vectors, what does that tell you? Because it's tempting to say, one of them must be secretly doing what the other is doing. And in 2014, that's exactly what a graduate student figured out. But we'll get to Levy and Goldberg later. First, the counter theory. Today's 3 beats. First, how GloVe actually works. Global co-occurrence matrix plus matrix factorization. Old linear algebra. New packaging. Second, why the results are near identical to word2vec. Same benchmarks, same clustering. Sometimes GloVe wins by a hair. Third, Levy and Goldberg, 2014. The paper that says word2vec is implicitly doing matrix factorization, which would explain everything. Beat 1. How GloVe works. Step 1. Go through your entire corpus. For every word pair, count how often they appear within a small window of each other. You end up with a giant matrix. Rows are target words. Columns are context words. Cell values are how many times target and context co-occurred. If your vocab is 50,000 words, that's a 50,000 by 50,000 matrix. Step 2. Factorize the matrix. This is the linear algebra move that count-based methods had been doing since the 1990s under names like LSA, latent semantic analysis, and HAL. You find 2 smaller matrices that, multiplied together, approximate the giant original one. Each row of the smaller left matrix is a target word vector. Each row of the smaller right matrix is a context word vector, say 300 dimensions each. Those are your embeddings. GloVe's clever move. The specific loss function, not just any matrix factorization. Pennington argued that ratios of co-occurrence probabilities are what carry meaning, so GloVe fits the vectors such that the DOT product of 2 word vectors approximates the log of their co-occurrence count, weighted so that very common and very rare pairs don't dominate. That's the whole recipe, and it trains fast, comparable to word2vec. Beat 2. Why the results are near identical. GloVe and word2vec were benchmarked side by side. The same analogy tests, the same similarity tests, the same downstream tasks. Result, GloVe won on some, word2vec won on others, but within a few percentage points. The gap between GloVe and word2vec was smaller than the gap between well-tuned and badly tuned hyperparameters within either method. That should feel weird. Not just the scores, the actual vectors. If you take word2vec vectors and GloVe vectors and align them, they're almost the same shape. King minus man plus woman works in both. Paris minus France plus Italy works in both. Cluster cat and kitten close together in both. 2 teams doing genuinely different math wound up in the same neighborhood of the space of all possible embeddings. That's the coincidence or clue question. Now, a caveat. GloVe has one practical advantage. It's easy to train on your own corpus if you already have the co-occurrence matrix. And Stanford released pre-trained vectors on huge corpora, Wikipedia plus GigaWord. Common Crawl 840 billion tokens. Those pre-trained GloVe vectors became a default download for many years. Even people who preferred word2vec's approach ended up using GloVe vectors because they were the easiest to grab. Beat 3. Levy and Goldberg, 2014. This is the paper that closes the loop. Omer Levy and Yoav Goldberg, two Israeli NLP researchers, sit down and work out the math. What they show is the specific objective word2vec skip gram with negative sampling optimizes is equivalent to implicitly factorizing a specific matrix, the matrix of shifted positive pointwise mutual information between word context pairs, which is, surprise, a rescaled version of the same co-occurrence matrix GloVe factorizes explicitly. That's why the vectors converge. Word2vec looked like a predictive neural net. But under the hood, the training procedure was pushing the vectors into a shape that could just as well have been derived from linear algebra on the co-occurrence matrix. The philosophical war between predictive and count-based was, it turned out, a war between two ways of doing the same computation, which was a great result and a slightly humbling one for both camps. So, what are embeddings really? This is the clue Levy-Goldberg gave us. Embeddings are a compressed representation of a corpus's co-occurrence statistics. Whether you get there by predicting or counting is an implementation detail. What matters is you find a low-dimensional geometry that preserves which words appear near which other words. That is a much cleaner conceptual framing than word2vec is a neural net that learns meaning. And it sets up the next video perfectly. 3 takeaways before the quiz. 1. GloVe, global co-occurrence matrix plus matrix factorization. Dot product of two word vectors approximates log of their co-occurrence count. 2. Results near identical to word2vec on every benchmark. Same analogies, same clustering, same downstream performance. 3. Levy-Goldberg 2014 shows word2vec is implicit matrix factorization. Both methods are compressing co-occurrence statistics. The predictive VS count war was a draw. Quiz 1. What's GloVe's central move? A train a neural net with negative sampling. B. Build a global co-occurrence matrix and factorize it so dot products approximate log counts. C. Delete rare words. Or D. Use transformers. B. Count then, factorize. The specific loss GloVe uses is a weighted least squares fit, where word vector dot products should equal log co-occurrence. That's an old linear algebra trick with a specific new weighting. Fast to train and easy to distribute pre-trained vectors. Quiz 2. How do GloVe and word2vec compare on benchmarks? A word2vec wins by a mile. B. GloVe wins by a mile. C. Within a few points on every benchmark, smaller gap than hyperparameter tuning. Or D. They score exactly the same. C. A tie, which is what makes it interesting. Two teams doing very different math wound up producing near-identical embeddings. The gap between them is smaller than the gap between good and bad tuning within either method. That's a strong clue that they're measuring the same underlying thing. Quiz 3. What did Levy and Goldberg 2014 show? A word2vec is broken. B. GloVe is broken. C. Word2vec's skip gram with negative sampling is implicitly factorizing a specific PMI matrix. Same math as GloVe. Or D. Nothing new. C. The unification. Word2vec looked like a predictive neural net, but was mathematically equivalent to a specific matrix factorization on co-occurrence statistics. Predictive VS count was a false dichotomy. Both methods are compressing the same underlying object, which reframes what embeddings actually are. Back to the puzzle. Two competing teams, different math. Same result. The clue is, both methods are compressing what co-occurs with what, which raises the deeper question. Why does co-occurrence carry meaning at all? That question was answered in 1957 by a linguist named J.R. Firth, half a century before word2vec. Next video. Next time, the distributional hypothesis. Firth 1957, Harris 1954. Why the whole thing works at all, and why the answer is stranger than you'd expect. Hit subscribe.